Good morning. Good morning, everybody. Thanks for being so prompt this morning. I know a lot of people are still not shown yet after last night, but we'll go ahead anyway. Many of the papers you've heard so far have referred to GÉANT and Internet2, and I think underlying or implicit in many of the advances we've heard has been the existence of high-speed, continental, and indeed intercontinental networks that provide the test beds for the developments we've heard of, whether it's the grid or multicast or video services or IPv6. All of them have, even if they haven't referred to it, they've relied on the existence of these high-speed networks. And at the same time, both GÉANT and Internet2 provide mission-critical production services for literally millions of students and academics in Europe and North America. So we're very fortunate to have two of the people who are instrumental in the design and rollout and operation of these networks, Davies and Guy Arms. Guy, I'm sure, is no stranger to many of you. He's managing director of DANTE, which represents or provides wide area networking services to the NRNs around Europe. And one of their services, and it's only one, although it is the keynote one, is the GÉANT network, which is a world-class pan-European network operating in the higher gigabit range. And I think Guy has obviously been with that from the very start. And even as we speak, I guess there are important developments going on in the GÉANT network. So I'll ask Guy to say a few words about the success of GÉANT, and I don't think he need be modest about that. It's been a tremendous success, and perhaps some of the underlying management of it, including the payment for the network, the cost sharing. So I'll hand you over to Guy.
Well, good morning, ladies and gentlemen. My name is Davies. I'm the General Manager of DANTE. And what I'd like to do this morning is tell you a little bit about GÉANT and the issues and challenges in building it and the benefits that come from it. I'd like, first of all, to comment on the title of this talk, Great Expectations about New Technology. This, in fact, wasn't my title at all. It was the title that was given to me by Mike Norris. Mike looked at the acronym GÉANT, and he came up with this really rather interesting breakdown of the acronym, Great Expectations about New Technology. A number of you will probably know the name Great Expectations. If you know anything about English literature, there was a famous 19th century writer called Charles Dickens. And Charles Dickens was responsible for the book Great Expectations. If you look at the state of the international telecommunications industry in the world at the moment, then maybe Great Expectations is an optimistic title to choose. Charles Dickens had another book that he wrote called Hard Times. And I think if you look at the current environment where we have 3 suppliers to the industry that have gone bankrupt in the last 6 months and a further 4 in Chapter 11, then you realize that maybe Hard Times would have been a better choice of novel from Charles Dickens to use than Great Expectations. And anybody who knows Hard Times will find the story, the title gives you the feel of it, that it's a very unhappy and rather a sad book. And at the end of Hard Times, the hero dies in the arms of his partner, and his final words are, "It's all a muddle." And if I look at, for example, some of the discussions going around the organisation of Framework Programme 6 in Europe, I think that phrase is actually quite an appropriate phrase. So given the free choice of titling this, I would have chosen Hard Times about New Technology and not Great Expectations about New Technology. But there we are. Just to give you a little bit of background about GÉANT, we set out about 18 months ago now to build what is in fact the sixth generation of pan-European research network. 6 generations in 10 years is actually quite a rapid rate of change, in fact. And one of the reasons why this has happened has been that historically, within Europe, telecommunications has been something that has been rationed, it's been controlled, and effectively has been expensive. With the liberalization of the marketplace, then we saw an opportunity really to build a network within Europe that took advantage of the latest technology and the most advanced routing and connectivity that we could get hold of. And so the original objective with GÉANT was to build a wavelength network. And when we started, we thought we could probably get about half a dozen 2.5 gigabit wavelengths. And in practice, one of the things that really impressed us was that the state of the telecommunications market in Europe today is such that you can get access to the most advanced connectivity at prices that are affordable. And so, in actual fact, what we achieved was a much bigger network than we originally set out to build. We set out with a relatively modest objective of building a network which had at least 6 2.5 gigabit wavelengths in it. And we ended up building a network which had 9 10 gigabit wavelengths in it and 12 2.5 gigabit wavelengths in it. So it gives you a feel for how far Europe has come on in terms of access to advanced networking technology. So that in itself is quite a significant success. The third bullet on the slide, though, also says something about the state of certain parts of Europe today. And that is that there is a considerable amount of SDH connectivity within the network. What is an interesting statistic to consider is that you've got basically 120 gigabits worth of wavelength connectivity and 3 gigabits worth of SDH connectivity. And if you look at the underlying cost of that SDH connectivity, even though it's only 3 gigabits, it represents 45% of the total cost of the connectivity in the network. And that shows you that although we've achieved a tremendous amount in Europe in terms of breaking down a lot of the barriers, there are still locations where connectivity is rationed. And so there are still some challenges there to overcome before the whole of Europe can benefit from the sort of performant network that GÉANT is. So we built a very large wavelength network, and because we built that network, we needed to find routers to actually be able to take advantage of the capacity we'd put in place. And we chose Juniper M160 routers as being the routing platform to complement the wavelengths that we put in place. This is the topology of the network as you see it today in what's really described as a tube map form. And I think what's important here is if you look at the black lines represent the 10 gigabit wavelengths, and you can see a double square of 10 gigabit wavelengths. And the red lines represent the 2.5 gigabit wavelengths. And there are some very encouraging aspects to this map. If you look at, for example, a number of the Central and Eastern European countries, you look at Poland, Slovakia, the Czech Republic, and Hungary, these are all countries that 5 or 6 years ago were struggling to get any connectivity at all, and now they're part of the most advanced connectivity that's available in Europe. But at the same time, if you look at a number of other countries, if you look at Greece, if you look at Portugal, and some of the Baltic states, you can see there is still quite a significant problem in getting all of these countries connected at advanced speeds. So GÉANT has represented a very big step forward in terms of making advanced network technology available for research purposes. But there are still pockets of Europe where there is a significant challenge to be overcome. Another way of looking at the map is to indicate the capacity that people are connecting to the network at. And essentially the red represents the 2.5 countries that are connecting at 2.5 gigabits. Ireland is a rather attractive shade of green, which I suppose is appropriate in some sort of way, but we're expecting Ireland to change to red in the not-too-distant future as well. And that gives you an indication of the state of advancement of telecommunications and of research networking in Europe. That shows you the access speeds of the countries. And I think a lot of the countries that aren't coloured red at the moment, that is essentially because of the inability to get the right sort of connectivity to those countries at affordable prices. If I look at the basic architecture of GÉANT, one of the things that we certainly discovered was that if you are implementing 10 gigabit wavelengths, this is not plug-and-play technology today. 2.5 gigabit wavelengths, yes, operators are familiar with those. They can basically commission them more or less in a routine sort of manner. But the 10 gigabit technology is a new technology, and each one of the wavelengths that were put into the network was essentially handcrafted. I think if you take the longest connection in the network, which is between Stockholm and London, that has over 50 regenerator sites in that connection, and each one of those required attention, and effectively the people installing that wavelength started at one end and went right the way down the wavelength at each particular site, tuning and making sure that the connectivity worked. So that 10 gigabits is yes, it's a speed that you can buy, but in practice today, it isn't routine technology. And I think that's one of the things that we learned, that at 2.5 gigabits, you're doing something in the marketplace that people are familiar with. As soon as you get to 10 gigabits, it's new technology. It requires a lot of effort. It's basically an analog technology, and so you go back to the good old days of load and worrying about attenuation and all of these practical factors, which means that just to implement 10 gigabits is quite a challenge, even for the professionals. One of the points that you will see in the network design is that we chose to use unprotected wavelengths. I think one of the lessons that we've learned over the last several years is if the telecommunications industry offers you something that is protected, you have to ask the question, what does protected actually mean? And in practice, one of the decisions that we made was that the protection that we wanted against individual link failure was something that is inherent in the GÉANT network because of the use of dual unprotected wavelengths, rather than relying on the assumption that if you buy something that's protected, if it fails, it's automatically replaced. Certainly our experience of protection is that it's a nice word, but it doesn't mean very much. And so one of the basic architectural features of GÉANT is that we use dual unprotected wavelengths in all of the locations. And in order to ensure that these unprotected wavelengths didn't represent a single point of failure, we put a lot of time and effort into actually looking at the physical routing of the wavelengths, looking at the straight line diagrams that we got from the providers to make sure that the physical routing was diverse, to make sure that at a duct level we didn't have any single points of failure. So in practice, in terms of the basic architecture, this first bullet, which sounds very simple, dual unprotected lambdas, is in practice a much more complicated thing than you might reasonably expect. The diverse routing of the connectivity is obviously an important factor as well. You have to ensure that basically, if you are relying on dual unprotected links, that you're not introducing a separate point of failure where those two links happen to be in the same fiber. So that's another factor which we put a lot of effort into, is to looking at the diverse routing of the connectivity to eliminate as far as possible single points of failure that would cause the isolation of parts of the network. The other thing which was interesting was in terms of the choice of router. We realized that we were using very high-speed connectivity, and there's not a lot of point in having that connectivity if you don't have a router that's actually capable of exploiting it. So you could have a 10 gigabit line, but if the router that you connect to it isn't actually capable of really filling that line, then there's not a lot of point in having the line. And so we looked for wire speed performant routers, and also wire speed performant routers that were capable of performing the range of functions that we wanted, from multicast to quality of service to MPLS. And that is essentially why we chose the M160 as our basic routing platform. It is a wire speed performant router, and it does enable us to run multiple functions in parallel on the same box without taking any performance hits. So these were the basic building block assumptions when we started off looking at the network and constructing it. And they're very fundamental architectural decisions that we made, and I think they've proved to be very sensible architectural decisions. Now, one of the important things was we weren't just building a network essentially for connectivity. We're also building a platform for development. And there are a number of areas of development that are going on in the context of GÉANT. So actually exploiting this advanced network technology. And you see the four principal areas of development that are current today. I must say that one of the things that you learn if you look at these developments and you manage them over a period of years, as we've been doing in DANTE, is that there is an enormous gap between technology and service. So you can have the technology, and the technology has certain functions. To convert those functions into a real service is actually a challenge of detail, it's a challenge of operational procedure, and it's a challenge which actually takes a lot more time and effort than simply implementing the technology. And so if the first of those, Multicast, is something that we started with well over 3 years ago. And in 3 years, we've developed the degree of sophistication in terms of the multicast service that is provided as part of GÉANT. But I wouldn't say that that is a production quality service today. And the reasons for that are not actually the technology so much as the way you have to implement that technology and the process and procedures that you need to put into place to make sure that you move from technology to service. So one of the developments, Multicast, is something that we've been working with for several years. We've improved the ability to offer multicast, but I wouldn't say that it's a production quality service yet. So an interesting perspective of how long it takes to get from a technology to a service. The second is something that is obviously very much in vogue at the minute, IP version 6. Obviously, IP version 6 will happen at some point. There is a requirement, a fundamental addressing requirement that will make certain that that is the case. There are a number of very big projects in terms of IP version 6 in Europe. One of the, GÉANT provides a basic platform in particular for the 6net project. But in addition to the big project, there is an interest in GÉANT in looking at a multi-vendor implementation of IP version 6. Because effectively, I think with IP version 6, it comes with a lot of bundled functionality which doesn't exist in IP version 4. But the one thing about IP version 4 that makes it ubiquitous is its simplicity. And I think the challenge with IP version 6 will be actually to get access to that bundled functionality that exists within the standards and the specifications. The challenge will be, will it exist actually in the implementations? And will it exist in a multi-vendor environment in the implementations? Or will IP version 6 simply be IP version 4 with bigger addresses? My starting point at the moment is that IP version 6 will be IP version 4 with bigger addresses. The challenge to bring the enhanced functionality which IP version 6 potentially has is in some ways similar to the challenge of implementing the multicast service. The technology is there. Creating the service out of it is a much bigger challenge than you might think. The third area which we've been doing quite a lot of work on is in terms of IP quality of service. And we have a project called Sequin, which was presented, I believe, yesterday, that shows some of the work that's been done in terms of IP quality of service. And interestingly enough, what we've been doing with IP quality of service is actually getting ourselves back to a position we were in 18 months ago with ATM technology. So one of the curious factors, which I think is interesting, is that the previous generation of research network in Europe was a combination of IP and ATM technology. ATM technology is not a fashionable technology, and it's a technology which has been unpopular in certain elements of internet circles. But it did have one or two strengths, and one of the strengths it had was it did enable you to manage bandwidth in a pretty effective sort of way. You can't run ATM technology at 10 gigabits in practice, and so we lost that capability, and we spent quite a lot of time seeking to replace it by using some of the IP quality of service techniques that have been standardized. And one of the things that GÉANT will implement, it will implement two flavors of IP quality of service, that one provides guaranteed performance at an interface and the other provides guaranteed end-to-end performance. So again, a platform for development, but again, the challenge is not so much in the technology as in the detail of implementation. And in the fourth area, we are looking and implementing MPLS as something that will provide elements of guaranteed bandwidth across the network. Of course, currently, that is on essentially proprietary implementations. There are also some other expectations that come with the GÉANT network, and in particular, in a European context, there is a lot of cooperative research and development in terms of projects typically supported by the European Union framework programs. This is another expectation that we have, is to be able to provide support for these projects. And in practice, again, it looks an easy thing to say, but the detail of implementing these things across multiple networks in a European context is actually quite challenging. And I think it's fair to say that we're learning a lot from actually supporting projects as to what their requirements are. A lot of it is technology, it's about performance, it's about reach, but a lot of it is equally about manageability. One of the other areas that we're working on in GÉANT is actually testing other routing platforms. We've got a combination of Juniper and Cisco routers within the network. I personally like to see a fairly lively market in terms of products that we're buying, and I think it's important for the industry and also for researchers that we have a better and bigger choice of routing platforms. And so we're actually doing quite a lot of router testing in the context of GÉANT, particularly with a box from Alcatel. And the other thing which has been important and successful in the context of GÉANT is a much greater integration between Europe and the rest of the research internet. Historically, Europe has really been a little bit the poor man of the global research internet. Slower speeds, more expensive networking. But with GÉANT, we've broken a lot of these barriers. And now we have integrated GÉANT with the bilene and HEAnet and Canary networks in North America to find a much more jointly managed global platform. One of the challenges of this global research infrastructure, though, is that the provider of it was KP and Quest. And so we've had a little bit of challenge recently in ensuring the continuity of service between Europe and North America. I think you'll see in the next few days that we've actually managed to do that in a relatively straightforward sort of way. But the fact that GÉANT is part of the global research infrastructure, in a way that historically there was a separation, now there is a joint management structure and much better connectivity between Europe and North America, which in fact will be further enhanced by an additional wavelength, shows that the global platform for research is becoming very much a reality, certainly in the context of North America and Europe, and increasingly Asia Pacific as well. I think, having said that, I've given a picture of things that are moving in the right direction. But there are actually some quite significant challenges, and both technical and commercial. I'd like to start with the commercial challenges in the sense that they're, in some ways, obviously, they're not quite so related to the technology. But in fact, the reason that a number of these commercial challenges exist is caused by limitations within the technology. One of the things that you find if you look at the GÉANT network in detail and you analyze it is that the capacity within the network, certainly on the wavelength part, is over 4 times the capacity that accesses it. Now, part of this is because we chose to have an unprotected wavelength structure for robustness. But we've got an enormous amount of spare capacity in the network, which it's in fact impossible to use today. And there is an interesting question, is who pays for it? Because it sits there. We've got basically a core which has got 120 gigabits of wavelength accessed by 30 gigabits of access capacity. People have to pay for that, and nobody wants to pay for something that's not being used. So that's one of the challenges that we face, is who pays for this spare capacity. Another similar commercial challenge is you take grids projects, then they have a relatively limited footprint typically compared with the footprint of the network. Now, if you subscribe to GÉANT, what you basically do is you subscribe to an access that gives you connectivity everywhere. It gives you connectivity right across the European network. It gives you connectivity to North America. All of these things are included in the package. But if you only want a part of that package, then there is a challenge. And effectively, this is one of the issues about grids. There are technical issues about supporting grids, but also there is a commercial issue about supporting grids. Because if the grid footprint is only for a subset of the structure of the network, then they don't want to pay for all of the things that they don't use. And this isn't about spare capacity, it's about geography. So another of the commercial challenges is how do you support very large bandwidth users that only want a limited subset of what you're providing? And I think it's fair to say, whilst we have some ideas about how to solve this problem, we don't yet have a solution. One of the other things that's interesting is there is a lot of bandwidth available at really quite popular prices. And for people that just want a point-to-point connection, then this is something we ought also to be able to offer. Today we offer a general purpose service which gives you connectivity to the rest of the world from a particular country. But we should also be able to offer a point-to-point capability. So for particular applications and for particular countries, you ought to be able to demand not a global connection, but a point-to-point connection. And then finally, in terms of certainly the European environment, one of the major questions is how do you offer things end-to-end? Because in Europe, any service is a combination of the pan-European backbone and the national research and education networks in the different countries. And this end-to-end question was not normally a problem on a pan-European basis, because the ends were usually more performant than the middle. Now we've got a middle which is really pretty performant, and some of the ends are looking distinctly unperformant compared with the middle. And so the end-to-end question, which used to be a problem, how do you get the middle to work, now starts to be a question of how do you get the ends to work. So there are a number of actual very significant commercial challenges that come out of the success of GÉANT. And also, there are a lot of technical challenges as well. And in a sense, the technical challenges are the mirror image of the commercial challenges. We've got a tremendous amount of bandwidth, but we don't have a lot of flexibility in the access to that bandwidth. And I think that one of the points that you have is basically everything is managed at a packet level. We have this 10 gigabit network, and the unit of management is either a per packet basis or it's a wavelength basis. And that's it. And there is nothing in between, really. So we have a lot of bandwidth, but we're not really very clear as to how we can manage the access to that bandwidth in a sensible sort of way. The next point is that we've chosen, for reasons of cost effectiveness, to use these really very big building blocks, these 10 gigabit wavelengths. And in practice, it says 25 gigabit lambdas. I managed to miss a full stop out from that, just in case anybody was wondering why we got this new speed that suddenly emerged. The practical point about how do you use the lambdas in an effective way? Basically, the lambdas simply sit there and they terminate on routers. And the ability to access and to manage these lambdas is a challenge that is for the future. That technology is not there today. And the whole ability to manage this network essentially relies on per-packet techniques today. One of the things that we really have to look at in the future in terms of the technical challenges is to get access to and to be able to manage the wavelengths, so that in practice, whilst we've chosen to implement things at 10 gigabits, it might be more effective to implement those wavelengths as 4 times 2.5 gigabit wavelengths, and to be able to route those individual wavelengths. That is a challenge. It's certainly not routine technology today. So there are some interesting areas there, particularly in terms of management, that now start to look interesting because we've got access to wavelengths. We've got access to wavelengths, we've got access to 10 gigabit speeds. Our management is still at the packet level. And that is one of the very big challenges that we face in the future. And in particular, how we can switch some of this wavelength capacity. These are the sort of future challenges that we've seen. One of the nice things in Europe is we have a platform in GÉANT on which to fulfill those challenges. But there are some very specific technical and operational and commercial issues that still need to be addressed because basically we have the technology, moving that from technology to service is the big challenge for us now. Thank you.
Thanks very much, Di. We'll take questions now on Di's session before moving ahead to speaker number 2. Questions? If it's okay, Di, could I ask you one question? I think you're aware that one of the effects of the whole procurement for DANTE has been to, I won't say totally shake out the market, but it has flushed out a lot of provision in the telco market, which national networks have been able to take advantage of. Do you see any way of formalising this so that after procurement of core capacity and access capacity, national networks could take advantage of any capacity that's available there?
Wired again for the sound. I think the difficulty that we face in terms of in a sense, the cost-sharing model is basically how you provide access to that capacity on a marginal cost basis. In practice, there is one subscription model today, which is the total costs of the network are shared, and they're shared according to the access capacity of the individual networks connecting. That doesn't work particularly well at the sort of speeds which we're currently implementing. And this spare capacity question is a very difficult question, because effectively everybody's paying for it, but nobody's using it. And then the question is, well, if somebody uses it, everybody else feels unhappy because they're not using it as well. And there really isn't a simple solution to this today. There are two requirements, in a sense. One is a very simple model for sharing the costs, and the other is a fairness requirement, which is a sort of usage-based way of charging. Now, the problem with usage-based charging is it requires an awful lot of time and effort to collect the usage and then to bill people back. And to be honest, the structures are not there in Europe to be able to enable us to do that. And so we've gone for a simple model, and the question is how can you bend that simple model, for example, to meet the requirements of people that only want connectivity between 4 or 5 locations without making them pay a share of the total cost of the network? And that's a challenge for us. We don't have a solution to it. I have some ideas, but there is no solution to that today.
Okay. Any other questions? All right. Well, again, thanks very much to Di for his first talk this morning. We'll move on now to our second speaker. Guy Alms is the chief engineer in Internet2, and I guess his creation, along with his colleagues, is the bilene network, which provides very high-speed connectivity for universities and others in North America. Guy's achievements go way back. He's had long experience and long acknowledgement as a pioneer in the Internet. But we're particularly pleased to have him here to tell us about latest developments in Internet2 and anything else he cares to talk to us about. Thanks, Guy.
Thank you very much, Mike. I'm very proud to be here. This is my second time to Ireland within the last year, and I would love to continue to make a habit of it. And I'm particularly pleased to be talking next to the presentation on GÉANT. I think that in many respects you'll see a lot of similarity between the plans for the upgrade to the bilene network and GÉANT. The similarities and differences are both very important. But I do want to spend some time on the bilene backbone, but also spend an equal amount of time discussing broader Internet2 and engineering issues. So in outline, the first half of the talk will be talking about the current and planned Abilene backbone. The second half touches on a number of engineering topics in the broader Internet2 area. And before I go into the first half, though, I would like to sort of rehearse for myself mainly why Internet2 and similar projects are important in the world. And at least within the US, I use this slide to remind myself of what's important. It's a twofold thing. First of all, to create superlative networks for the universities in various respects, and secondly, to make sure that they can be exploited by users so that networking, high-speed advanced networking becomes a strategically valuable thing for university people in their research and teaching. And I think that we're well on the way around the world to accomplishing that. The current network is based on a 2.5 gigabit per second infrastructure that's very important to, it's very important for the success of this network that was built on a partnership. The Internet2 project partners with Cisco Systems, with Juniper, with Nortel Networks, with Quest Communications. The NOC is supplied by Indiana University. And also, finally, we have 2 test and evaluation centers, one in North Carolina and one in Ohio. And it's of extreme importance to find these partners, find strong partners who are willing to make this project their own. All have been superlative. The current network is an IP over SONET backbone, designed in 1998, became operational in 1999. 2.5 gigabit per second is called OC48 in the States. Right now, there are 53 direct connections to the backbone. By direct connections, we refer to, in some cases, direct connections by campuses. Most of the time, however, they're direct connections by what we call gigapops, which are regional or metro area, state area, cooperative structures that aggregate access to the bandwidth. 4 of those connectors come in at the full OC48 line speed. One of them is currently coming in with a Gigabit Ethernet access. The remainder are 622 megabit or 155 megabit access. Some of them are ATM-based access to the backbone, and that's slowly decreasing with time. Out of those 53 direct connections, they support 215 participants. About 200 of them are Internet2 member universities, but also there are a few federal labs and corporate laboratories. And we have participants in all 50 US states, the District of Columbia, and Puerto Rico. Out of those 53 connectors, it's probably important to stress that a small number of them, namely 15, support about 70% of the participants. A more recent thing is we've had a thing called the Expanded Access Program where we have 50 different sponsored participants. It's very interesting from a pricing point of view. If you're a member of Internet2, then this stuff costs you a certain amount of money to share in the cost of Abilene and to participate in the network. But if you're a member and have a connection, you can bring along a friend. These are typically libraries, museums, laboratories. Examples are the American Museum of Natural History with its HEAnet Planetarium, which is a very modern planetarium that's basically an I/O device for NCSA in Illinois. So some of the most superlative computer graphics powered by supercomputers 500 miles away is sort of the new way to build a planetarium. The Smithsonian Institution is another example, by the way. International connectivity is of great importance to us. This first bullet is a little bit tongue-in-cheek. It is true over the long term, transoceanic research and education bandwidths have been growing. And the 2 OC48 circuits that DANTE has caused to come into being are of enormous importance. The needs of applications, the needs of users to access and collaborate with partners across the university world are not limited to any one country. So the idea that between Abilene, DANTE GÉANT, and the ocean between them, you can get end-to-end performance that is equivalent to what you could get within any one of those backbones is a very pleasing result of the last few years of improvement. The question mark at the end of the first bullet is just sort of a worry I have. We depend, of course, upon the health of our carriers, and it's of great importance to work with these carriers this next few months. I very much appreciate the work that Di himself has done this last few days in helping to recover from one particular dependence. Exchange points are very important. The StarTAP and Starlight projects in Chicago have been of key historic importance. And right now they're very important for how we connect, for example, with SurfNet. The AMPATH program is a relatively recent project of Florida International University and Global Crossings to get to at least 45 megabit per second access to each of several different Latin American countries. The Pacific Wave Exchange Point in Seattle is a project of the University of Washington, and that's afforded great connectivity to Australia and to the Far East. ManLAN is a planned exchange point in New York City based on Gigabit Ethernet and 10 gig E. We connect with the Canadian networks in Seattle and Chicago and New York City, and that's of great importance to us. And finally, we connect to the Mexican research and education backbone, both in El Paso, Texas, and in Southern California. There's a thing called the International Transit Service, by which we, within Abilene, provide connectivity between, for example, networks coming in from Europe, from Latin America, and from the Far East through the Abilene backbone. And that's of great value in avoiding a situation where non-U.S. networks would be otherwise compelled to come to a single point, such as Chicago, for their international connectivity. And we do this in collaboration with the StarTAP project and with Canary. And this is a map that has two values. One of them is to show the current OC48 topology, and secondly, to show all of the points at which we have international connections. It's a bewildering set of connections. I think in some respects it's going to become more systematic now with the advent of GTRN and so on. Now, in terms of the current backbone, before I go into the plans for the next backbone, it's very important to talk about what application groups can do when they have everything on the local end done right. In January of this year, there was a demo done largely by the University of Washington, University of Southern California, ISI, Tektronix Laboratories, under DARPA funding. They were trying to do raw HDTV at 1.5 gigabit per second end-to-end across the country. And so this ran from Seattle, Washington, to the ISI East laboratories in Arlington, Virginia, across the backbone, across the Pacific Northwest Gigapop, across the Max Gigapop in Washington, D.C., end-to-end. This is running at a steady 1.5 gigabit per second at the application layer, ran for 18 hours, and the application software detects packet loss and out-of-order packets. And over this entire 18-hour period, they detected no packets lost and only 15 episodes of resequencing, that is, of packets delivered out of order. This is something that I would never have imagined in my wildest dreams. It shows what can be done when everything is right. By the way, there are numerous Juniper routers and Cisco routers in this end-to-end path, several different carriers, and a bunch of people doing hard work to get things right. Now, in terms of that performance of 18 hours, 1.5 gigabit per second, no loss, you can project statements about at certain confidence levels what the loss rates are. And Steve Corbido did some math and did a projection that you had 0.8 packets per billion lost at the 90% confidence level. And he turns this into a projection of what you could do in TCP performance. To get 1 gigabit per second TCP performance, you require less than 30 packets per billion lost. At standard 1.5 kilobyte frames and a more relaxed one at 9 gigabyte frames. He's basically showing here that this is a network that can achieve gigabit per second TCP performance. So this is an example of what happens when everything is done right, and we'll talk more about that later. However, the typical experience that users detect is nowhere near this good. This is a graph showing a cumulative distribution function of bulk TCP performance measured by net flow statistics across the Abilene backbone. And it shows, among other things, that the median experience of bulk TCP flows is only 2 megabits per second. This is quite a contrast from 1 gigabit per second and suggests that things are not always right at the endpoints. Okay, in terms of the future of Abilene, the original cooperative agreement with Qwest Communications would have run through March of 2003. It's now been extended to October 2006. And there's an upgrade underway now based upon that amendment and extension to the agreement with Qwest, under which we're going to shift from OC48 SONET facilities to 10 gigabit per second unprotected lambdas. This is a 4-fold increase in core backbone bandwidth, of course. And this is the planned topology of the new network. In this network, the green color from Indianapolis, Indiana to Atlanta, Georgia shows a residual OC48 circuit that's going to be kept in place because there are no lambda facilities along that physical path. And that path is very valuable to us for redundancy and for low latency traffic between the Midwest and the Southeast. The red circuits are 10 gigabit lambdas that will be part of what we call phase 1, from Washington, D.C. to New York, Chicago, Indianapolis, Kansas City, Sunnyvale, California, and then up to both Seattle, Washington, and to Los Angeles. The blue networks are part of phase 2, which we hope to have in place by the middle of 2003. Some of the causes for phase 1 and phase 2 are just, it's very hard to do things all at once. Some of the causes have to do with particular regulatory situations whereby Qwest is currently unable to provide new long-distance facilities in the Rocky Mountain states, and we expect that to be taken care of by the time that we need phase 2 to be in place. But this is a topology of the 10 gigabit per second network. It's very, very similar to the current 2.5 gigabit per second network, with the exception that we've removed the core node in Cleveland, Ohio, and changed the circuit paths around between New York and Chicago a little bit. But it's very much in the same style of a partial mesh of point-to-point circuits that we're familiar with since the days of the ARPANET. One of the major things we've done this spring is to select a successor router for use in the upgraded network. We did extensive specification and testing of both Cisco and Juniper routers. We wanted to make sure that we really did avail ourselves of the very best router technology. The tests focused on next-generation advanced services, including high-performance TCP IP throughput, multicast IPv6 functionalities and throughput, and the ability to classify packets very rapidly. We don't have a particular QoS service planned, but we wanted to make sure we selected a router that was capable of doing the core functions that you need to support QoS effectively. We tested 3 different router platforms, the Juniper M160, Juniper T640, and the Cisco 12400 series, and did a bunch of discussions with people who had used those platforms, and in the end selected the Juniper T640. It's very pleasing to have a choice among 3 different good choices, and it's a very nice time to be buying routers. We're continuing to work on procurement of various components of these things. Each of the 11 racks, each of the 11 nodes of the new network is going to be 2 different racks of equipment. About half of one rack is the T640 router itself. The remaining 1.5 racks is mostly test equipment. We're trying to put in the ability to study this network and understand it very deeply. Racks will be assembled during July. We'll be deploying the phase 1 racks during August, September. The first wave of lambdas will be commissioned during the fall, And then we're expecting to be able to support at least these two demonstration events. One is the Internet2 Fall member meeting in Los Angeles in late October. And also SC2002 is in Baltimore this year, and that's in mid-November. We'd like to be able to support very aggressive applications of the network in support of those two activities. Then during the first half or so of 2003, the remaining lambdas will be commissioned. In terms of ways in which the new network will differ from the old network, we're talking about just a few things. The most important one is native IPv6 as a first-class service. In the current Abilene based on Cisco 12008 routers, we're very pleased with our IPv4 service in terms of its performance and reliability. We want to provide that same kind of performance and reliability for both v4 and v6 equally in the upgraded network. Motivations for doing so having to do with address exhaustion issues, of course, but also we want to make sure that we preserve the end-to-end transparency and global addressability that are part of the IPv4 internet that we've built over the years. I wish I could say that it's inevitable that that will be preserved with v6. I fear sometimes that if we don't do a good job on v6 and do it fairly soon, there might be alternatives that we might like a lot less based on NAT boxes and such things, where you'd lose that architectural transparency, and that would cause us to suffer with respect to our ability to innovate in applications. So we're trying to make sure we do a good job of this. International collaboration with people who are very strong in the v6 world, including both in the Far East and also in Europe. So we're going to be running dual stack v4 and v6 in the Juniper routers from day one. And in this respect, we're hoping to replicate the strategy we deployed successfully in 1999 with regard to native IP multicast in the v4 world. We found that by doing a good job on IP multicast in the backbone, that accelerated the support of multicast in the gigapops and campuses. And we'd like to repeat that same success with regard to IPv6. A second emphasis is on network resiliency. We benefited greatly on from the 2.5 gigabit per second circuits that Quest provided us using Nortel Kit. It used full ring protected circuits, and there were many amusing examples where the protection, as Di pointed out, does not always buy you what you imagine it would. But over time, that got debugged, and we're very pleased with it. We're using unprotected lambdas now, and that's going to be very important for the future. There isn't any really practical alternative to that. It will mean that we need to be able to converge very rapidly whenever there is a change in the topology of what circuits are working right now. And this is exacerbated by the fact that we're having an increased use of video conferencing and voice over IP applications. So we'd like to be able to recover within a small fraction of a second from circuit outages. So we'll probably be using MPLS initially as a way of achieving this. We hope to work hard with Juniper and Cisco and others to work on the implementations of OSPF and ISIS interior routing protocols in order to converge very rapidly in a pure IP way so that we don't need to rely on MPLS for this functionality in the future. And then thirdly, we want to support a deeper capability for measurement in the past. We have these two racks. A majority of the space in the racks really boils down to one way or another measurement equipment. We have 4 dedicated Unix servers in these racks. Some of them have Gigi interfaces right into the T640. Others go through an Ethernet switch into the 640. And we hope to be providing the ability to measure TCP throughput, UDP throughput and latency, and so forth. This is of very great importance to us to fully understand the behavior of these networks. Also, with some passive measurement capabilities are very important. Taking these things all together, we want to understand the network deeply, both for operational purposes and also to make the network an object of study by computer scientists who are trying to understand the phenomena that surround high-speed wide-area networks. And that's led to a notion of Abilene observatories, where it's currently just a sketch of an idea. We want to improve the ability to gather data, put it away, archive it so it can be used by others, but also to provide for direct network measurement and experimentation by network researchers. So we've reserved space and power in these racks for 2 additional machines of the kind that we're building 4 of, and we're leaving them vacant in order to permit scientists to come to us with proposals for what they would like to put there. And I have a hope and a fear that this will happen very, very soon. But we'd like to see that succeed. We'd like the network to be an object of study so that computer scientists and other network researchers can help us to understand better how these things all work. So in summary, the upgrade's underway. Partnership with Quest is extended through 2006. Juniper T640s are the routers of choice. Lambda deployment is something we'll learn all about this fall. The advanced services foci include native high-performance v6, enhanced measurements, and network resiliency without ring-protected SONET. And we hope this is going to be an incremental and not a disruptive transition. Okay, so that's Abilene backbone. In fact, I might want to pause there and ask if there are any questions about the backbone itself. It makes an interesting comparison with GÉANT. Mike?
Go ahead and use my privilege and ask a question. You spoke about trying Gigabit Ethernet access. What are the main factors you'd be looking for there in comparison with existing SDH access?
Good question. Mainly, we want to really understand whether it's going to be something that gives very low loss and can handle multicast well. These things are not entirely obvious. This is nominally a LAN technology, and we want to make sure its performance, reliability are adequate for our needs. The example, by the way, is in Chicago. The same group that engineered the Starlight structure are the technical leaders within the Gigapop in Chicago. And they had nice fiber capacity within Chicago. So just doing a straight single-mode fiber into the backbone router in Chicago seemed to make a lot of sense, and Gigi was a nice way to do that. One of the issues with Gigabit Ethernet, by the way, that's very important to us has to do with the MTU. I'll mention in a few minutes. We really like to experiment with MTUs greater than the 1,500 byte IEEE limit, and I'll talk more about that later. But there are some important issues in that area. After years of critiquing and criticizing ATM, we're now learning that there's lots to criticize about Ethernet as well, so we'll have to be very careful about that. Okay, let me go into the second part, and then we can have questions about the whole... Oh, I'm sorry. Yes, sir.
Can you say a few words more about your attitude to a different level of studies? It was mentioned that here in Europe we put stress on providing some sort of guarantees for very critical services. I know that the US is different.
Right. I would like to answer that after the second part. And if I don't, be sure to remind me, because that's an extremely good question. And I'll be talking about our current work in QoS and in end-to-end performance. During the second part, and the way those two things weave together is a real story here. Let me talk a little bit about multicast. Recall that in 1998, the native IP multicast routing protocol sort of existed within the IETF. Deployment was very rare. The early M-bone tunneled structure was no longer a scalable thing. And yet at the same time, multicast was regarded as key to new generations of applications. So we used the emerging standards of PIM sparse mode, MBGP, and the MSDP protocol to support native IP multicast beginning in spring of '99. And that's continuing to work very, very well. The map showing here, this is not something you have to study in detail, but it shows that on a large majority of our campuses, at least part of the campus LAN supports native IP multicast. And we can do great things with this. We can do very high performance multicast very reliably. So we're pressing on with deployment more and more. Applications and contents. It's very important to us to learn what about multicast is of value. What are the applications that are going to make that worth paying for in the commercial network? And improving scalability. And on the point of scalability, I wanted to mention this thing called source-specific or single-source multicast. In classic IP multicast, you create groups, let's call it G, and those group IDs are 32-bit values that have global significance. There can just be one multicast group of a certain bit pattern. Any given user on the internet can create those things, join it, and start sending to it. Other users around the world can join that same group and listen or send to it. And it's the duty of all the routers around the world to make sure that all those people who have joined the group are receiving all the packets sent by any one of them. This is pretty hard, and the triad of MBGP, PIM sparse mode, and MSDP is required to make that all work. And it does work. There are issues of scalability, however, and those issues of scalability, in my view, are improved quite a bit by source-specific multicast. You have these same notions of group values, but they have purely local significance, a little bit like a TCP port number. So user S can create one of those groups, and the thing that he creates is called a channel, and it's really the 64-bit catenation of the source unicast IP address and that 32-bit group value. And others can subscribe to and listen to that channel, but only S can send to it. And so that means right away that there's no need for MSDP, which has to do with discovering the sources of traffic into a group. There can only be one source into S, G, and that's S. So MSDP goes away. Any notion of allocation across the world of these G values goes away because they're purely local significance. So lots of issues become easier. This is going to dramatically simplify multicast routing and addressing. It'll complicate life for some of the applications, such as the access grid applications that sort of lean on that global G value for lots of different purposes. But the requirement to do that additional work at the application layer is really an opportunity to get a few things right, including security, authentication, and so on. So this is some work, and one of the really hard things here also is it requires a new version of the IGMP protocol by which hosts join it. And this is a lot of work for the multicast working group and the vendors that support multicast. We hope to learn some things about that. In fact, there's one view that I'm tending to favor right now, that source-specific multicast might be a sufficient version of multicast for all applications of multicast. And if that strong view is true, then we might want to specifically go in the direction of supporting source-specific multicast and eventually turning off the current model. I mentioned V6 in context of the backbone already. We continue to work to understand the motivation for IPv6. Talking about the exhaustion of the address space is difficult in the States because all of our member universities have these wonderful Class B address blocks in V4. And it's hard to get their attention in some respects. But we're working on that. And we're doing a lot of work in deploying, improving the engineering expertise in V6 on our campuses. And we're stressing the need during 2002, 2003 for supporting V6 as a first-class service. The backbone upgrade will result in a backbone capable of first-class performance. And it's becoming very evident that all of the current versions of Linux and Windows XP and so forth can support V6. And if the applications are there, that might result in a very sudden demand by students and faculty for V6 support. So this is a much sparser map showing the very weak deployment of V6 right now. It's currently based on tunnels, V6 over V4 tunnels going through some Cisco 7200 routers. Functionally, it's adequate for the current usage. Used some very good work by Cisco last year, can support applications up to 34 megabits per second, which is quite remarkable in a tunneled environment. But those times are past now, so we're trying to move toward really first-class service. One thing we're trying to do is do training workshops. We have about a dozen of them this year in total. These are 2-day workshops, about 20 people each in several different parts of the country, and they're being very well received. We've been asked to have a few of these in Australia as well, which we're doing this next month. So we want to make sure that people get some IPv6 experience on every one of our campuses and prepare at the same time for native IPv6 peering, both between the backbone and gigapops, between gigapops and their campuses, and within key parts of campuses. And it's not just a matter of addressing and routing. It's equally important to get the applications, domain name system stuff, and operational stability right. So that's all important work. Now for a little talk about current state of things in the QS area. It's really this is currently receiving less intense work than it did 1 or 2 years ago. In retrospective, our initial work on quality of service emphasized the thing we called premium service, in which you had end-to-end, I'll say guarantee in a soft sense, but essentially an end-to-end guarantee of very, very, very low loss and almost no jitter end-to-end for selected applications. In hindsight, we viewed that as being a bit too ambitious. It put much too great a demand that all of the routers in the backbone be able to police all of their interfaces with regard to this kind of traffic. And it also put too great a demand on the ability of our peering networks to coordinate. So both the policy drivers of how much, who was allowed to use it and so forth were difficult. And then enforcing those policies proved to be very difficult with the current generation of routers. But in saying that this was very hard, it's not the case that if it were necessary to do this, we would probably continue to work on it and do it. But there's a couple of implicit claims in this judgment. And one of them is that during the entire time when we were having a continuing difficulty trying to implement premium service, we were discovering that even very, very aggressive applications were able to achieve excellent performance end-to-end, provided that they got their end parts right. So it appeared to be the case that at least for a period of time, over-provisioning of backbones and other parts of the network, plus the removal of end-to-end performance problems that are typically caused by non-congestive sources of packet loss, if you do these two things, then you can get the same kind of end-to-end performance you might have associated with premium service, even if you're just using best efforts service. A second point is an implicit claim that it's important for applications to become smart and to learn how to adapt to certain things. What is receiving a lot of attention by the Quality of Service Working Group is a couple of non-elevated services, by which we mean services that are QS services, but they're not the classic QS service that promises that your packets will be more important than everyone else's. The first of them is kind of an odd thing. It's called the scavenger service. It's less than best efforts. You might wonder why this is attractive. Some people have truly massive amounts of data they'd like people to move around, and they're a little bit worried about what happens if they do that daytime using best efforts service, but they're worried about causing congestion all over the place. So in a way, it's kind of nice to be able to have truly massive data transfers, mark them as less than best efforts, and then have the assurance that they won't interfere with the time-critical applications of others. Less far along is some work in what we call alternative best efforts service. We might want to mark your packets as being loss-sensitive or delay-sensitive, but not both. Now, this sounds very simple, but the basic idea is, could you do this in a way and then handle those packets in a way, queue them differently, and do that in a way so that neither of those two classes was globally better than the other, but they provided two different kinds of best effort service. If you're able to achieve that, then you'd have a situation where users would have no motivation to lie. They would just mark it according to the nature of the usage that they're making of the network. And that would remove any need to police ingress traffic or shape outbound traffic. And that would retain the simplicity of the current best efforts model with regard to administration and policy. So this is a matter of ongoing work. And then finally, elevated services like premium service can be deployed locally. Sometimes a campus or gigapop will know where there is congestion, know that there is congestion, know where it is, and then do specific ad hoc things locally to avoid congestion for certain applications there. And this can receive experimentation and even use. It's nice that it doesn't require end-to-end coordination of policy. And so we're kind of trying to work on this right now and observe it in practice. So the current, let's see, yep. So that's the end of the work on discussion of quality of service per se. We regard it as of enormous importance in the long term. As a statement about the present, we just don't see quality of service as being the big thing that inhibits successful deployment of advanced applications. What does inhibit that is this thing I'm talking about in the next few slides that we labeled the end-to-end performance problems. We discovered that people can push multi-hour 1.5, 1.6 gigabit per second flows with very, very little loss and reordering if everything is right at the endpoints in the backbone. And yet user experience varies dramatically from that. This is a huge mismatch. So here's a couple of things. What should we be telling our users about the end-to-end performance that they can expect? We could just bluff them and say that it's easy, okay? 80 megabits, easy, okay? But that doesn't always work. We could just say we want to lower their expectations and tell them that it's, it's just the internet, and you never can tell what you'd get, and don't even try to do ambitious things. And that would be very nice in some respects because people would stop complaining to you, but they'd probably also stop funding you eventually, right? So candidate answer number 3 is the one we've chosen, which is to try to raise their expectations, encourage the users to try very ambitious, aggressive applications, and then work with them to make them work and discover how to do so. So things that cause end-to-end performance to suffer. If you'd asked me in 1997 what are the major threats to end-to-end performance, I would have said congestion and wide area lengths. And we're not saying that now. We're seeing instead stupid, non-congestive things like dirty fibers, inappropriate attenuation, Ethernet switches and ATM switches that just lack horsepower or that get confused about whether they're full duplex or half duplex. Inadvertently stingy provisioning. This is another word for congestion in a sense. But the problem is, what if the funding source that might remove that congestion isn't really convinced that congestion is the real source of the problem? So really knowing that the problem is congestion is key. Bad routing. It's amazing how easy it is to do the wrong thing in this area. Host issues are a big issue to us. Cheap network interface cards, bad TCP stacks, just I/O buses and CPUs on the host systems, and getting it all working together well. It's emerging that even a majority of the end-to-end problems are really problems within the end host machines. So put these things all together and you get a perverse combination of two things. The users imagine that the network's congested. What they see is similar to what they would expect to see if the network was congested. So they blame Internet2 and they blame GÉANT, I'm sure. And they're so, and they're not always aware of the nature of the backbone, so they think the ARPANET's still congested. At the same time, network planners look at utilization charts. Because of these end-to-end problems, utilization is less than it could be. And so they conclude that no further investment is necessary. And the fact that both of these could be happening at the same time is ironic, but it's true. So we're working hard on measurements, coordination, understanding, so that we can rapidly diagnose end-to-end performance problems, point the finger at what is wrong. In a large majority of cases, these problems are difficult to diagnose but trivial to fix once you've diagnosed them. And so that's our hope. At the same time, I do want to touch on one thing that I'm going to say now that I might not have said even 2 or 3 months ago. The TCP layer, the transport layer of the protocol stack is receiving a lot of good attention right now. Much of it takes the form of improved implementation of the old TCP protocol. The Web 100 project within the States is one nice example of that. New parts of TCP, such as selective acknowledgement, window scaling, and a related thing called explicit congestion notification are very important to this world. The hope is that if you do all these things, then you can more fully utilize these very wide area, very high-speed pipes. But still, there's some fundamental limits. In some analytic results, TCP throughput is expected to be proportional to MTU and inversely proportional to round-trip time and to square root of packet loss. The fact that the MTU is still stuck at the 1500 byte standard of 1980 is kind of a problem. We'd love to have larger and larger Ethernet MTUs, IP MTUs. We're currently supporting 9,000 byte MTUs within the backbone as one step in the direction of improving that, and trying to work together with other networks so that users could have 9K byte MTUs end-to-end would help a lot. There's not much you can do about round trip time, short of improving the speed of light. I'm sure someone's working on that. But the fact that the bits are coming more rapidly to us than they did before, but they're still just as slow as they ever were in terms of propagation delay, is a major concern. So I think that that there are some ways of addressing some of these fundamental issues. But one possibility is the need to supplement TCP with future work on transport protocols. And the real key issue is the bulk data transfer thing, moving very, very large data sets in support of grid applications, high-energy physics applications, and others. So there are related ideas, transport-level gateways. I can talk to people about this if they're interested. But also in the future world, we imagine sometimes that you'll be doing less statistical multiplexing. You'll know more about the allocated bandwidth of pipes end-to-end. And that might allow improved transport protocols also. So that's the end. Now back to your question. So I think, in a sense, the answer is sort of implicit in what I was saying at first. In '97, if you'd said, what's the big problem with performance going to be, I would have anticipated wide area congestion. And given the realities of 95, 96, 97, that was a reasonable concern. The response to that concern was a QoS effort that emphasized explicit handling of high priority traffic, so that if it is a high priority application, you forward it, queue it selectively, give it preferential queuing, and then that removes the problems due to congestion. Before we succeeded in that, we had two different experiences. The positive experience was discovering that with the OC48 Abilene backbone, with the new 10 gigabit per second networks, you can do truly marvelous things in an ordinary best efforts network, provided you do everything right. That's the good news. The bad news is that it's hard to do everything right. And the real nightmare would have been if we had spent a lot of money building a carefully orchestrated quality of service structure that gave preferential queuing to high priority traffic. But if we had done so and at the same time neglected to solve those end-to-end problems, just because you queue someone preferentially doesn't mean that they're not going to be killed by duplex mismatch on Ethernet switches or dirty fibers and things. So those same problems that cause these end-to-end performance problems are problems that would have killed your effective performance in a QoS-enabled world. So even if we had done all that QoS stuff and deployed it, the applications would still have been killed when they tried to achieve that end-to-end performance. So that's the short version. This statement about over-provisioning and best efforts being good enough is not necessarily a permanent statement of reality. For example, the people who do work in TCP implementation give us a wink every now and then and say, once our new improved TCP implementation comes out, we're going to congest your 10 gigabit backbone very nicely, okay, and use it all up. And they say it with a smile and good grace, but in a way they're very serious about it, and it might actually happen. If the applications and transport protocols become able to really use up that wide area structure, then we may need to go back to our QoS ideas and work hard on them. So we're not neglecting that in the set of ideas that we work on, but our emphasis right now is on aggressive provisioning and end-to-end performance diagnosis.
Well, thanks indeed, Guy. Are there any questions? Roberto?
Just most of the comments were on your quality of service discussion. One is a question on Multicast building. Well, we've done a lot, as you know, a lot of work on quality of service in Europe, and one of the main points that has kept us insisting on trying to get this IP specification done and implemented is that IP, from our point of view, does not necessarily guarantee better performance than best effort can. better than the That's one of the things that I kept us working on it.
Yeah, yeah. I think that it's very well motivated to work on it. Okay? If someone were to say to me, I want to deploy voice over IP today within the internet, what should I work on over the next year to make sure that I can do a good job on it in operational practice during the next 1 or 2 years? I just would not emphasize QoS in response to that question. So we're studying it. As I mentioned before, when we did the selection of the 10 gigabit per second routers, we did a lot of study of the ability of the 3 different router candidates to do the fundamental QoS mechanics very efficiently. Because we intuitively believe that you're right. The day's going to come when we're going to need to do these things, and we need machines that are capable of doing them. It's just that it's not a current emphasis operationally. And if someone's having problems with if someone's trying to use the network in an aggressive way and they're having performance difficulties, we don't want them to rapidly come to the conclusion that, oh, the reason this is not working is that it's best efforts IP, and if I only had QoS, things would be different. It may not be true. It may be the case that what's killing you is not lack of QoS, but some stupid, non-congestive source of loss. Yeah.
The other question I had was more towards Multicast.
Yeah.
I see you've done a lot of, well, you have done, as we have done, a lot of technology deployment. What steps have you taken to make the service deployment of Multicast, operational production, product service? Have you done any experience there?
It's really, the answer is so, we just turn it on and let people use it. Okay. Yeah, so basically, I guess that's a service in the same sense that our unicast IP service is a service, you know. People use it. Now, in the current classic multicast model where if any sophomore in a dormitory creates a group and starts sending to it, then that allocates a slot in all these routers. If we were to have the number of people using multicast double and then double and maybe double a third time, we might begin to realize that problems with the any source multicast model were going to cause problems for us. In the commercial world, people are very reluctant to just turn this thing on because they're worried about what happens. So far we've had essentially no problems that are attributable to people just misusing it. We had, in fact, you can sort of imagine some interesting denial of service attacks based upon aggressive use of multicast, and it's kind of scary to imagine that. The only problem we've had that was even close to that was really not, there was one of these denial of service attack virus kinds of things that happened, and it wasn't intentionally trying to exploit multicast, but there are these things called port scans, right, you know, where you send packets to a series of addresses. Just pick a block of addresses, a range of addresses, and send packets to all of them and see what happens. There's different UDP and TCP ports. Someone did this to us, and they clumsily made the mistake of sending it to a range of addresses in Class D. And what happened is that the multicast routers interpreted that as people creating and sending to a whole bunch of groups in this range. Because every one of those distinct Class D addresses was a new group. So the routers throughout the Gigapop and campus and backbone were furiously using MSDP protocol to share with each other the latest knowledge about this new set of groups that have been created. And that was the biggest example of an operational problem caused by misuse of the protocol, and it was totally inadvertent. Someone being irresponsible with it in a way that they didn't understand. So we do want to keep an eye on the scaling of multicast and hope that we're able to keep one step ahead of the demands in that area. Yeah. Yes, sir.
I found an interesting difference in approaching bandwidth managing programs within Internet2, in the sense that in GÉANT, we are looking at replacement of activity using MPLS-like techniques. Replace the bandwidth, reduce the bandwidth more efficiently. Whereas I understood from your presentation
Internet2 is actually looking at modifying the transport protocols to achieve the same result. In a way, over-provisioning takes the infrastructure for granted. It's there.
Yeah.
Just add some more bandwidth. And the problems lies more in the protocols and the applications and so it's less useful to split the bandwidth, to use better the bandwidth. Yeah. I would like a comment on that.
I think you've given a very good comment yourself. I have nothing to criticize in the way you've cast the problem and the way that Di discussed it at the beginning of the session. But there are, it's so hard to say what the right thing is. At one point, Di was saying that you have these 10 gigabit per second trunks in your backbone, and that's, I forgot what phrase was used, Di, but it was sort of like this was excess capacity and who's going to pay for it. I thought to myself, that's not excess capacity. That's capacity that's making sure the people who come into you at 2.5 gigabit per second are not going to experience congestive loss within your backbone. That's a wonderful thing, you know. If you were to use ATM and MPLS and quality of service and all the machinery that you could bring to bear to guaranteeing that those 2.5 gigabit per second access feeds would not encounter congestive loss over the wide area, provisioning 10 gigabit per second circuits might be the cheapest way to accomplish that. Who knows, okay? I'm not saying it's true. I'm saying that it appears to be true for the present. And furthermore, I would say that even if it's not true, it's a very nice way to present to your users a challenge to aggressively use the GÉANT backbone in a way that sheds light on innovative, future aggressive applications, while at the same time we at the network layer are learning how to use MPLS and QoS to make that more methodical. Both things are important, but it's very nice to have a platform for users to use the network very aggressively, while at the same time we learn more sophisticated ways to provision capacity. And I want to say that I've been using the internet before it was the internet. I became a computer science grad student at Carnegie Mellon in 1974, and there was this thing called the ARPANET, you know. And I've seen the ARPANET from 74 morph into NSFNet and the internet now. And every generation of this network is a partial mesh. The maps even look alike, you know. Look at the NSFNet T1 backbone maps. They look very much like bilene or GÉANT, you know, just partial mesh topology among nodes, routers, point-to-point circuits. Very nice. And what changes over time is the bit per second rates. So we've gone from 50 kilobit, you should see these battleship gray 50 kilobit modems of the ARPANET, okay? And now we have 10 gigabit per second unprotected circuits that are, they're called lambdas, and it's cool to call them lambdas, but they're just point-to-point circuits, okay? I have a feeling that that's about to come to a screeching halt. That when we talk 5 years from now about the successor to GÉANT and the successor to bilene, what we're going to see, I think, is going to be those same 10 gigabit per second circuits, but more of them. We start to see bundles of 10 gigabit per second circuits rather than a single partial mesh of 10 gigabit per second circuits. With the ability to do optical switching within the fabric, that's going to present us a dramatically different engineering problem of how to effectively use those raw materials instead of the raw materials that we're used to using. And that's where a lot of what we learn from the early use of MPLS and traffic engineering and so forth today are going to feed into the concepts for how to effectively use those bundles of lambdas in the middle and late part of the decade. And that's going to be a very interesting, exciting period of time in which to do network engineering. I won't pretend to know what the right approach to that is. People in Canada have some ideas. People in industry have some ideas. We'll all be made fools of, I'm sure, but it'll be fun times. And one of the basic ideas is that you're going to have these bundles of lambdas. It's one trend that's very clear is that you're going to use optical switching to take little segments of fiber and knit them together into longer point-to-point circuits that in the limit might get very close to the endpoints. And so people even talk about running lambdas straight from host to host. And I doubt if it will ever get quite that far. But you will have longer distance lambdas that come closer to that and reduce the number of separate IP hops. So gradually less statistical multiplexing and packet switching, gradually more circuit switching, to use an old-fashioned phrase, and optical switching. Where it all leads, I don't know. I think it'd be very exciting to work in this area during this decade. So the current bilene and the current underway upgrade to bilene, along with GÉANT, can be viewed in, I think, as really the last generation of evolution of partial mesh IP networks going back to the pre-IP era. And they work very well. And it's very important for users to aggressively exploit their wonderfulness, because if the applications people shed light on what's valuable and useful and fun and interesting at the application layer, we'll find some way to support it, whether it's a QoS or what. So.
Okay. Once again, thanks, guys. We've just come to half time. The third speaker is scheduled for this part of the program. Unfortunately, was not been able to get to Limerick. However, Jordi's paper on cost sharing, the Marley cost sharing algorithm from Barcelona University is on the website, on the training website. So people are more than welcome to study it there. So once again, thank you for coming along, and thanks to our speakers.